Thanks for having me. It's actually fun. So I'm not a theoretician, but I love hanging out with theory people. I always learn a thing or two talking to theory folks. But I like to joke that theory people solve problems they know how to solve. Systems people solve problems we want to solve. And somewhere we need to find that mix. Okay. So this is actually a line of work that is actually in collaboration with, mostly done by Victor, who's a PhD student at UNC, and Mike Reiter, and funded through AITF, which is sort of funding all of these things. It is actually one of the proposals that we submitted. We did not call it intent-driven optimization at that time. The buzzword came much later, but I guess now in the context of intent-driven networking, it sort of fits very well with that theme. Okay. All right. So as we've seen, sort of the context for this work is we've seen a number of talks here, a number of papers at SIGCOMM, NSTI, Infocom, your favorite CONEX networking conferences, that we see a lot of applications in networking that essentially require some kind of network optimization, traffic engineering, service chaining, placement of nodes, and so on and so forth. And I've done a bunch of these papers, I've done a bunch of these things, and we've written a number of these kinds of papers. Now the problem is, solving these problems is just pretty hard, right? If I actually want to take any of these algorithms that have come up with these algorithms or think about these, I actually need a lot of smarts as a network operator. I need to go implement these things in some complex optimization frameworks. I need to be a super smart theoretician. I need to look up CLRS or read like Dexter's book. And I'm like, okay, damn. I can't even get started if I'm a network operator. I need to be a super smart theory PhD to even get started on these problems. And this has actually bugged us, right? If I try to write this paper, 6 months of my time is spent in sort of coming up with interesting theoretical formulations as opposed to sort of core network problems. So the current process, which we have done multiple times, is sort of a hair on fire process. I take a bunch of, send my students to take theory optimization courses. They try to formulate this problem. They solve it with the solver. They say, oh, damn, it's not fast. Then they think about whether it's NP hard. They start developing heuristics. They don't quite work. Then they have to actually eventually they find a heuristic that actually works. Then they go like, okay, how do I get this solution and implement it inside an SDN controller and whatnot? And then they say, okay, fine, now maybe I can deploy something. Okay. All right. It's actually a pretty painful process. Like, so networking students don't like math, right? There's like, the minute you actually see like SIGCOMM reviewers, if you have to say, okay, they just gloss over your entire ILP formulation and say, oh, there's some fancy looking math here, it's probably right, and let me move on in life. Okay. Sorry.
Sounds like you're saying the math never works out anyway, so you could just make the process just painful by skipping the first 4 steps.
Unfortunately, that's what networks do today, right? And we don't want that state to happen. Unfortunately, we're not even done here, right? So we're actually not done. The reality is actually not even done. So we've talked about a number of different sub-problems today, but the reality is in actual network, you don't just have like one sub-problem with like one paper or one SIGCOMM paper, right? They actually have like 20 different applications, 20 different things. They have a security team, they have an operations team, they have a backup team, they have like all sorts of teams, and they have to worry about, and we talked about with Harry's, like how do all these things compose together, right? How does my security application, my firewalling application, my service chaining application, my accounting application, how do they all compose? And it's actually a painful sort of task. And this is kind of where sort of this is the status quo. We all talk about this sort of intent-driven networking and this buzzword about AI and self-driving networks and so on and so forth, but actually we are in pretty primitive stages. So this is the vision. Again, I have more questions than I have answers, right? As a systems person, as I told you, I have questions and I go and say, hey, help to my theory folks. So this is the vision of this, what I call intent-driven optimization, is really to have, again, so systems people, our standard answer is to add like another layer in the stack or add another layer of indirection. We hope that the world will magically solve itself. So I'm going to add what I would call an optimization layer that somehow magically will solve this problem. And essentially, with this, I can sort of help network administrator focus on their intents or their high-level goals, help them rapidly prototype software-defined, self-driving applications, cool stuff, and also make it easy for them to think about composition of these different things. Okay? This is the holy grail where there's this sort of common platform. I come and write these very simple programs, and what I can essentially do is put theory folks out of business, right? I want to actually take the network operator who does not have to be a theory PhD. They can actually be like a Dilbert, an average engineer who can come and write these, and hopefully some of us have developed these optimization layers to make their lives easier. Okay? I don't actually want to like put theory folks out of business, but if this vision takes off, hopefully sort of a lot of the theory will actually go in there and sort of make these things sort of enable this future vision. Okay? So this is the goal, right? And if you actually think about where we are, it's actually pretty hard to achieve this, right? If you think about the current workflows, people either use like off-the-shelf optimization frameworks like Cplex or Gurobi, or they develop these custom solutions, and all of them have this sort of fundamental trade-off between generality, efficiency, and composition, right? I can write an ILP or an LP for pretty much anything I want, but it's very general. It may not be efficient. It does not let me compose things. I can develop like custom heuristics, like I'll come the best bin packing for some placement problem. It's not going to be general. It's going to be efficient, but I'm not sure how I can compose these and so on. What I really want is the sort of bottom row that gets me all of the above. Okay? And what I'll tell you in this talk is a little bit of like the preliminary work we've done in this space to at least get somewhere along the way in solving these problems. We're not done there. Okay? I'll try to talk about sort of two pieces of work. One is a system called Sol. It's an SDN optimization layer. And another sort of builds on top of Sol to say, hey, look, once we bring a common abstraction layer, how do we enable composition capabilities on top of it? So, and sort of this is kind of the vision of intent-driven networking. And we're going to almost argue that going to this intent-based model makes composition a lot easier than otherwise. Okay? Again, there's a lot of sort of related work here. I'm going to gloss over, but I'm happy to talk to you about other related work in this space. In fact, there's some work out of here. Merlin was out of Cornell, which actually is very much aligned with some of this vision. All right. So what is Sol? So Sol essentially was this sort of intermediate layer or library that we wrote that made it easier to prototype different kind of software-defined optimization applications. Okay? So if I have a traffic engineering application, if I have a service chaining application, and we've written a number of these sort of individual tasks, we want to create like this high-level API. Think of it like a domain-specific language for writing network optimization tasks. So you write it once in the Sol language or in the Sol API. Sol takes care of all the nitty-gritties of how to deal with solvers, how to deal with scalability. Again, this is the vision, right? I'll get you sort of how we actually do it. And then it sort of interfaces with your SDN controllers to actually install the routes and so on. So you as an operator can just say, here's a 10-line program. I want traffic engineering, and magic, it happens. Okay? So this is sort of very aligned with sort of the SDN sort of vision, and we actually want to support a diverse set of applications. So the one question we had was, what should this sort of Sol API be? How do I support a diverse set of applications, like traffic engineering, service chaining, load balancing? They're all pretty sort of different. And this is one of the observations that we had in Sol, and sort of just looking at a number of emergent papers that we had seen, was to revisit a very classical sort of formulation and said, look, we can write a lot of the common applications that people want to think about in networking as essentially path-based applications. Okay? Again, if you think about MaxFlow, there's sort of two canonical versions of MaxFlow. I can write an edge-based formulation of MaxFlow, which is very compact. You talk about flow conservation constraints. You can also write a horribly sort of expanded, combinatorially large, path-based formulation of MaxFlow, which says, okay, how much flow am I sending on every single path? You can enumerate all possible paths. Now, that edge-based formulation is obviously very, very compact, but it's actually hard to express additional kind of tasks. If I want to say service chaining or waypointing or load balancing or other kinds of like predicates on what this path should satisfy, it's extremely hard to encode it in the compact edge formulation, but it's trivial to encode it in the path-based formulation. I can just say, hey, this path has a firewall, it's okay. This path seems to have 4 hops, it's okay. Those are all sort of very nice, simple predicates I can write on top of those paths. So that actually seems like a very expressive abstraction in which we can say, as a network operator, I can essentially specify, and we've seen this in several of the talks here, right? Sort of this path emerges as a natural abstraction for writing network applications. So we just said, let's go with the path-based abstraction because it lets us capture a number of possible papers, a number of possible optimization tasks that people want to write. Okay? So that's what we went with. And once we went to sort of the path-based, it became very trivial to express a number of policies we wanted to write. Right? Policies like, hey, if I want this traffic to go through a web proxy, a firewall, and an IPS in some order, this is actually what is called service chaining in the sort of the networking world. It becomes trivial to explain service chaining as a path policy. It's a very simple, like regular expression like predicate that says this path is valid, this path is not valid. So I can enumerate all paths and just mark what is valid and what is not valid. Okay? So, okay, so I've solved to some extent the expressibility of the API problem. I can just write, you just come and tell me what paths are valid. I can essentially write your problem as a path predicate. Okay. Now, yeah.
It's not clear. Are you saying that you're always going to assume there's a regular language that distinguishes the valid from the invalid paths, or is that just one example?
That is what we're going to assume. That's the early version. I'll get to. This is what Sol does, but I don't know if that's actually fully general. But it covered a lot of the sort of the current set of papers that people are writing that we looked at. So, and again, it's actually I think similar to what I think Merlin also uses a regular expression. It seems like a very powerful language for this. Okay, so this again, quote unquote, gives us generality, at least generality until what we had seen so far. Right? Is it general for future? I don't know yet. Of course, paths are a bad idea when you think about efficiency because you've suddenly sort of blown up the problem. What could have been a compact LP, you made it like a really, really large LP or a really large ILP, and that's actually pretty bad in practice. I don't want that because if I want to run traffic engineering and recompute my routes as dynamics happen in my network, I don't want to spend like 2 days computing these solutions. And this is kind of where we came up with a somewhat interesting heuristic and sort of based on empirical observations, which was that we actually don't need to write this sort of massive all paths LP or all paths ILP. What we could do was essentially sort of prune the set of paths that we actually use at runtime. So what we did was, in an offline steps, we would sort of generate all possible paths. Okay? We sort of do the combinatorial explosion of all possible paths. So this is an offline step. And then at runtime, what we'd actually do is we would sort of pick a random subset of paths. So what we just said was for every origin-destination flow, or again, think of it as a commodity in the sort of multi-commodity sort of abstraction, we would pick a random subset of paths or pick k shortest paths. And for most applications we saw, for some reason, 3 or 4 random paths or 3 or 4 k shortest paths of the shortest paths seem to suffice for most of the applications we picked. I don't have a theoretical reason why this happens, but it seems to happen for most of the workloads and most of the topologies we tried. And actually, that's an interesting sort of question I've been asking sort of any theory person. I said, have you seen this, right? You kind of saw this in SMORE as well, right? You actually don't need all the paths. Somehow, a small number of paths suffice, and there seems to be something there. I don't quite know why it's happening. But I was happy with the solution because it seemed to work for most things we cared about. So once we have those subset of paths, the online part just writes a very much more compact LP or ILP that just takes this pruned space of paths that I picked, random or shortest, depending on the applications. So the intuition was that either your applications cared about latency or they cared about congestion. For the congestion part of type things, random worked well, and for the latency type things, shortest path worked well, and somehow that seemed to work for most applications we considered. Okay. So we write the sort of the linear program. I'm not going to go to the details. I'm going to go write the linear program as a path-based formulation at runtime, throw Gurobi or Cplex or your favorite solver at it, and then I can just use the outputs, parse them, and feed the rules into an SDN controller. Okay. All right. So we implemented all of this. It's a Python library. It interfaces with a number of solvers. We prototyped a number of applications, right? We sort of looked at this, just one sec. We looked at a number of SIGCOMM and SDI proceedings and said, oh, here are a bunch of papers and so on that we saw. How do we implement them using the Sol API? I'll give you an example. Yes, question.
Just to your point about why you pick a subset of paths, it's an unsolved, just to make sure I understand, it's an unsolved problem to solve something like multi-commodity flow with regular expression constraints?
I don't know how to write like a max flow plus regular expression constraints. It's not a natural API for me. I don't know how to sort of.
But that's what you're trying to do, just to make sure you understand.
First selection. So you can let the Gurobi or a subroutine to the Gurobi select the pass for you. I don't know if you tried that. Like you can write the subroutine that will have Gurobi pick up extra pass if he thinks it's useful. Like revise simplex. I don't know.
So we've not looked at, we've tried to play around with different simpler solver options, and it didn't quite work for us. So we did play around with a number of solver options. We've tried like solving the network, there's a network flow solver and other kinds of solvers inside Gurobi. But again, I'm not a Gurobi expert, right? So it's entirely possible that we could sort of internalize some of these insights into the solver, but we haven't quite seen it.
So you would have to write the subroutine that helps Gurobi fix the relevant
Sure, but in some sense we are doing it
So
in the
I guess
opposite.
my suggestion, my take would be that, yeah, of course, pre-selection, so you can start, so something has to be useful, and then, but then I think you can put it into Gorobi, that if extra paths are needed, please feel free to pick them.
It's possible, it's entirely, yeah. So your question was like, I think at least I've tried writing these sort of formulations as like how do I add like service chaining to like a multi-commodity flow. There's some work out of Princeton that tried to do this. I think like Moses and other people have tried, maybe you're, it's actually very painful to write those formulations. And I mean, it doesn't look.
Wait, like, sorry, this is an open problem, I think Bobby told me.
Sorry?
Is that true?
You want to do pre-computation of a number of paths, so that supported on those paths is a good solution to multi-commodity flow for whatever like actual multi-commodity flow problem you're later given.
Yeah.
You want to do better than what you would get if like pre-computing and oblivious routing.
Oh, for undirected graphs, you can't do better than log.
Even with the polynomial. Oh, so it's
Even with a
not.
polynomial number of paths, and even if the graph is a n by n grid, it's depressing.
Okay. So that'd be a negative answer.
It's entirely possible, but I think the question is it true for all graphs, right? So there might be something about the graphs we see in practice in networking or the workload we see in networking that actually.
Just pass satisfying a regular expression. Can you do that?
This is good.
You can find that, that's a separate thing.
You guys can converge and give me the answer.
Shortest pass to satisfying a regular expression. I don't know if I can do that. But
Potentially, the best way to use our time is to let Ben get to the end of his slide deck and then continue this discussion.
I'm good. I mean, this is great. So I have problems, right? So you have solutions, so which is great. So I would let you run to convergence and give me the answer. That's fine. So here's an example, right? So essentially, it's a very small sort of Python program to write like traffic engineering. I don't need to worry about the solver. I don't need to worry about the routes. So it's a very, again, yes, lines of code is a horrible metric, but it's like the best bad metric we have. So it's like a very compact expression of like traffic engineering, other kinds of things we can write. So essentially say what kind of traffic classes you're interested in, what kind of like link constraints, what kind of capacity constraints you have, and what kind of like predicates you want to impose on the paths. And it's actually a pretty simple API to write these kind of optimizations. Okay. All right. So we can actually sort of solve these things, and this is you can specify an objective function and so on. So we showed that we took a bunch of these applications that we.
That slide was illustrating the code that the network operator would write?
Yeah.
I see. And how to lambda determine it?
That's Python, yeah.
Okay.
I'm not a Python. Well, this is, yeah, I think Victor was a Python fan. I would not have written Python, but Victor is a Python fan. So, yeah. So again, so basically you can write a number of papers. Essentially take, these are all published Sekar, NSDI, Unix papers. You can essentially take them and say we can write them in like 15 lines of code. You can essentially sort of trivialize a lot of these things and make their life easier. Okay. Again, take lines of code always with a pinch of salt, but this is kind of what it is. Again, I won't go into the result, but actually we said that with this pruning heuristic and this path selection heuristic, we actually get like near optimal as opposed to running like this sort of the whole paths are running in runtime and pretty good scalability. Again, it's not great for like data center scale networks, but for sort of ISP scale or overlay scale networks, it's actually pretty fast. That's sort of the high level stuff. Okay. All right. So this was our first step, which said that we can take whatever 15 papers that were written and trivially write them in 10 lines of code using the Sol API and get equivalent efficiency time trade-offs. Okay. But that actually is not the biggest win, I think, of writing to this common API. The bigger win, I actually think, it comes from when you start thinking about a system or a network that has like multiple applications, and how do you compose these multiple applications? And I actually think that making everybody write in this sort of common intent layer makes composition easier. Why do I say that? So today, actually, we actually don't have good models for composing different network resource optimization applications. Okay? So the best bad ideas we have right now are things like statically slice the network. So basically say if there are 3 applications, you get 1/3 of the resources, and I statically slice you. I can do like ordered optimization, right? Say you go first, take your pick, occupy as much as you want, you're rank second, you're rank third. Or there have been some sort of complex voting schemes that people have proposed in the networking literature. Okay? These are all what I would call output-based or output-driven composition approaches, which is you take a algorithm, you take the rules or the outputs it gives, and then you try to compose the outputs. Right? So it's basically saying that I want these kind of rules or these kind of paths in the network. You tell me these are the kind of paths you want, and then I'm trying to compose the outputs. And I feel like output-driven composition is like sort of fundamentally flawed. What we really want to do is like elevate the level of composition to the intents as opposed to the outputs. And this is kind of our approach. It's like once you have an intent-based approach for expressing these different applications, it becomes much easier to coordinate how you compose applications. Right? It actually becomes much easier to identify resource constraints or conflicts or other kinds of things ahead of time rather than wait for the outputs of these individual tasks. Okay? So this was a system that sort of followed on Sol called Chopin, which is a composer, pun intended, which said, how do we compose different SDN applications on top of a Sol-like API? And here we actually focused on sort of a couple of subproblems, looking at how do we compose these different applications and write like composition operators, as well as looking at sort of adding robustness to traffic variability, right? So when you wrote the sort of the Sol API, we didn't actually have to worry about like different traffic from different applications having variability or interactions with each other. But when you actually try to compose different applications, like say there's a backup application that runs at night versus like a DDoS application that runs during the day, they may actually have like different traffic workloads, and you have to start worrying about traffic variability across time and space. Okay? So we need like sort of robustness to traffic variability. Again, it sort of connects to some of the work you've seen earlier. Okay? So we retain the Sol API as before, right? So we sort of thought that Sol is a nice API. It sort of covered many different applications. But when we started thinking about composition, we needed to rethink the optimization functions and the way we did path selection and so on. And how do we sort of support composition, right? Rather than just these static allocation or like voting or prioritize optimizations, can we support like more class of like fairness objectives, right? So networking people like maximum fairness, hierarchical fairness, sort of this kind of like different kinds of fairness objectives. How do we support them in the composition logic? Okay. All right. So what we had to do is sort of we did a slight tweak to the Sol process. If you recall, we had like path generation, path selection, optimization, and rule generation. We kind of made a sort of a slight tweak where instead of doing sort of path selection per application, we sort of came up with a unified path selection logic. Okay? And the idea was the following: if everybody picked shortest paths, you're going to like congest those shortest paths, right? Maybe it actually makes sense to take your intents and say, okay, look, you all don't need to go down the shortest paths. You can get close enough to your optimal if you're slightly rerouted and so on. So we actually don't have everybody independently pick the same k shortest paths. It's useful for us to tweak them a little bit and do a unified optimization. Again, this is the benefit of intent-based composition as opposed to output-based composition. Yes?
So if application A says all of our paths have to go through a middle box of type A, and application B says the same thing, but they have to go through a type B middle box, is your unified coordinated selection going to generate paths that go through A and B?
Oh, no. So the applications are still sort of isolated. So it's just that imagine that if I ran Sol for A and B separately, so application A and application B, they would have picked all shortest paths through A and all shortest paths through B, and maybe one link got congested. But maybe in the unified selection, I say, look, you get shortest paths, semi-shortest paths through A and semi-shortest paths through B, such that the link does not get congested. So I'm not trying to compose the policies, I'm trying to compose the applications. You could also imagine other things of like composing policies, but that's outside our scope.
So I think about the kinds of examples that Michael was talking about yesterday, robotic surgery or CNN video delivery, where like he actually did want the lowest possible latency, and including he was going to like spend high cost to get that.
Yep. So you can actually write that. You can actually write that, right? If you can actually specify like a path predicate saying, I don't want more than 3 hop paths, that could be part of your application logic when you specify in the Sol API. So those are hard constraints and there are soft constraints, right? So you can actually specify.
The people who are doing these voting schemes were trying to reach some kind of equilibrium where everyone, has a conversation and then sort of makes bids and
yeah, we actually did compare against voting schemes, and somehow this is working better because you're actually not looking at the outputs that they came up with, but I'm actually looking at what you wanted to do, right? So I'm telling you I wanted a low latency path ahead of time, as opposed to saying, here are the rules I give you. And then composing the rules is somehow worse than composing the intents that you came up with. I don't know if that's fundamental, but that's what we saw in practice.
Seems like if the intent language is rich enough, then people can actually write things that are both flexible enough to enable this kind of composition, but also rich enough to express their constraints, sure. But I can imagine it's in practice easier to write an algorithm that participates in some kind of auction or bidding process.
I'm not so sure, yeah. Again, yeah. I'm taking a little bit of a dogmatic stance that it actually makes sense to force everybody into the same intents for composition. Yeah. I think the voting scheme makes sense if you actually have, like, say, a federated model where, like, you're actually getting, like, apps from different vendors and you're trying, this is the best thing you can do is to take the outputs and have them vote. But if you're actually having, like, one operator like Google or Facebook and there's just multiple competing apps in the same language, it's easier this way, right? All right, so it turns out, again, there's a little bit of a challenge here in terms of the online optimization. We have to have, like, we support, like, different kinds of fairness metrics. Again, anything that can be linearly combined, like maximum fairness, hierarchical fairness, many of these things can be written easily in this fairness model. And the other thing, since we write a unified optimization, it sort of automatically identifies sort of conflicting edges or conflicting nodes where the resources are constrained automatically, as opposed to waiting for the outputs in some sense. So you're writing like a unified LP or unified ILP for all applications, as opposed to writing individual applications or LPs. The offline path selection becomes a little bit more complex because you have to worry about, like, variability in the demands of different applications, and you have to worry about, like, sort of the problem size grows significantly as you have these different kinds of applications and so on. So we had to do a couple of heuristics. Again, we could use, like, oblivious strategies or other kind of strategy. I don't know what that means in terms of composition. So what we ended up doing was, like, a couple of heuristics. Again, there's some, I don't know if I'm going to talk about it. So I don't have time, but there's some parallels to the scenario-based pruning that we saw earlier. So what we ended up doing was take a bunch of these traffic matrices and said, like, we can cluster the traffic matrices and say, these look similar, so these are the kind of scenarios we see, and we can't solve this large discrete optimization problem, so we ended up throwing, like, a simulated annealing heuristic to find those paths. Okay? Not a very clever idea, but this is the bad idea we had. Okay? This is where I have, like, questions to ask a few. So again, I don't know how to do these very well, so we came up with this clustering-based things to prune out scenarios out of the traffic variability, and a very simple simulated annealing logic to say, how do I do this unified path selection for the offline optimization problem? Okay. The unified optimization is before we just use, like, this online solver and throw it at it, except that we've sort of composed it and we've added a fairness term to your objective function. Okay. So this is actually a paper, again, sort of this code has been implemented and integrated into the Sol sort of logic and the Sol language. So I'd sort of encourage you to sort of play around with it. We've compared it with a number of different schemes like static allocation and voting. I forget what it's called now. Corybantic? Yeah. No, well, I guess the published version is called Athens or something. Corybantic was the Hartnett's paper, but we compared against, like, our implementation of, like, Athens, Corybantic. That's the voting scheme, and we somehow found it actually find better efficiency. It also can better handle, like, traffic variability. Again, it's not perfect, but it does better than other options. All right. So we kind of got, I would say, like, 30% of what we wanted to do, right? So we got a little bit of generality, a little bit of efficiency, and we sort of said, once we do this, we can actually do better composition than the current state of the world, and that's kind of where we are right now, right? So getting the benefits of these kinds of SDN logic actually requires a lot of optimization knowledge, because at the end of the day, you're all solving hard resource management problems. And I would argue that this kind of an intent-driven framework kind of lowers the barrier of entry for development, not just for research, but also for, like, actual production and actual transition. And actually, maybe that's the way I think about, like, if you're sort of a theoretician who has a cool idea, it might make better sense to sort of adopt one of these frameworks or think about composition style problems as opposed to sort of individual style problems if you're looking to transition these things into practice. Okay. We have very preliminary ideas looking at this sort of path abstraction and pruning and some of the scenario-based pruning that we did. And we got to some level of efficiency, not data center scale. We can do, like, hundreds of nodes, but not 10,000s of nodes, right? That's sort of where we are right now. What I really wanted to come to is this slide, which is where are we right now and what do we need help on, right? And some of the conversations we've had, I'll just leave it out there, and we can talk about it, right? So we talked about paths, but there's certainly applications I can think of, say from a security context or like a dynamic context, like people want to do things called dynamic service chaining, not just static service chains. Like saying, if traffic has a particular, dynamically in real time, you observe an event, I want to spawn off a new path for this particular traffic. So that's called dynamic service chaining. are paths sufficient for dynamic service chaining? Do you want to route over subgraphs? Do you want to route over DAGs? Those are all questions I have. I don't have a good sense of why this path selection works. I think Mike, you also had something about like 2 and 4, right? You pick like 4 graphs and 2 paths, and somehow these small numbers seem to work in practice. I don't have a good reason why. I'm happy to take it, but I'd like to know why. So is there a better theory behind it? I mean, I've talked to some of my theory colleagues, and they think this might have something to do with expanders. I don't know. Maybe it has something to do with expanders. I have no idea. So why does a small subset of random or shortcut suffice? So yeah, like some graph-based solvers, would that be something to plug in here? Or some of the ideas here is like, okay, can I put these insights into like a Gurobi-like solver and say, these are better flow solvers or better network flow solvers? I don't know. I have serious scalability problems. I mean, every time we submit this paper to NSDA or SIGCOMM, people are like, you can't handle data center scale. Like, yes, we can't handle data center scale, but that's not the only world that exists. But we'd like to go there. So can we get to data center scale, which is tens of thousands of nodes? Or can you do some of the hierarchical sort of decomposition strategies and get something better, right? I don't know. I'd like to sort of better understand the traffic variability and robustness, especially what does it mean to do like oblivious, semi-oblivious stuff when you have like composition, when you have like different diverse demands. I don't know what to do. Maybe there's some elements of like probabilistic or fault correction that you want to add here. Yeah, I need help. Thank you.
Okay, so for short talks, we'll just do Q&A in the traditional way. People have questions? Absolutely.
Have you thought about use as OL in the traditional distributed routing network?
In a traditional distributed routing network, that's saying in terms of writing these things and then sort of compiling them to like OSPF rules or other kinds of things, that would be cool. We haven't thought about it. So because for us it was easy to plug into SDN and say here are the rules that you want to do. Maybe there's a way to reverse engineer and say these are the OSPF. Actually, people have done this. Right? There's been maybe Jen probably knows this more. Back in the day, AT&T had a bunch of these papers that would say we want to do this traffic engineering thing, and then here's this like roundabout way of generating the OSPF weights actually generates the traffic engineering objective. Maybe some of those things might be useful.
Yeah, although I'd imagine the regular expressions are going to mess you up very quickly, right?
No, once we have the paths, how do I sort of say that once Sol or Chopin gives you like, here are the paths I want, or here are the things I want, then can you sort of do the OSPF weights to generate this path?
A single weight on each edge may not be, maybe over-constrained.
I see.
There may be no setting of the weights that satisfies the service chaining goals, for example, right? That would seem
That is
to
possible.
Yeah.
But we can constrain the problem in some sense, right? If you say that all service chaining happens in a few locations, then we might be able to solve this problem. Yeah. But I think there's been some work by Forts and Thorup from, you should look at the 90s Infocomms. They've done all this work. AT&T has the AT&T research or Bell Labs folks have solved many of these problems. Yeah. But yeah, good question. I don't know how to do that. Yeah. Yes.
I just want to understand the bottleneck for the scalability. Is it the Monte Carlo simulation that creates the bottleneck for scalability?
Right now, the bottleneck is actually our solver, right? So we're writing this massive. So imagine you have like, say, a 1,000-node network. You have like, say, 1,000 squared commodities. So we have like 1,000 squared origin destination paths. And for each of them, I have like, say, 5 paths. That's like 1,000 squared times 5. There are at least that many variables in your ILP. It's just a massive problem. So it's not about Monte Carlo. It's just like I'm writing like a giant LP and ILP and hoping the solver can solve it. I mean, the solvers have gotten pretty damn good, right? I mean, when I first started, I was like, okay, I started looking at using Cplex and other things when I was in grad school, and at that time they were pretty bad, and we had to come up with these custom algorithms. But the solvers have gotten pretty good over time.
So somehow you have a constraint per path.
So the path constraints are actually, no, we actually have like how much flow am I routing on every path to model the latency and model the congestion and so on. So imagine if I wanted to write max flow as a path, instead of f sub e, which is like the flow on each edge for each commodity, I'm going to write the flow on each path for each commodity. So that's the spread out we are getting here. Yeah.
Maybe Kevin can help me out with this question, actually. So on achieving compositionality with scalability, like, people in the ECE control community have looked at these optimization decompositions
Yep.
where you have many simultaneous optimization problems, and you
Yep.
kind of have a thin interface between the high-level optimization. So it's neither fully output-driven, where you run the low-level optimizations once and then just combine their outputs, but it's also not throw everything into one big solver and do it in a centralized manner. So if you thought about incorporating those techniques into...
I've never understood this line of work, sorry. It's just, this theory beats me. I'm not smart enough to understand this theory, so I won't use it. So I've tried many times to understand this theory. I've never quite gotten close, so I just won't use it because I don't understand it. So if somebody can explain it to me, like, I'll be happy to use it. So, okay, maybe that comes back to that. It's like, okay, yeah. So, yeah, I've tried to read these papers. I've never understood. I failed over like grad school. I've stopped trying. So maybe I'll get a smart grad student who actually understands them. Okay, maybe. Sorry. So this is the kind of thing that, so I'd love to understand that, but I don't know.
Sounds like a great thing to discuss over coffee.
Thank you.